Hey, how visible is it when I do that? Can you see that pointer? Yeah, okay.
Second session is Nate Bottman. He will talk about which trees and the Kontsevich operator.
Okay, thanks for the introduction, and thanks to the faculty for organizing these talks. So, whoops. So I'll tell you about these which trees in the Kontsevich operator, but let me start with some context. So very quick intro to symplectic geometry. A symplectic manifold is an even-dimensional manifold with a closed 2 form whose top wedge power is everywhere non-vanishing, so it's a volume form. In the case that n is 1, that's just a real surface with an area form. There's a distinguished class of important submanifolds called Lagrangians. These are half-dimensional submanifolds with the property that the restriction of omega to that submanifold is 0. In the case that n is 1, that's the same thing as an embedded curve in our real surface. At least if those Lagrangians intersect transversely, is a linear combination of intersection points. Now, in order for this to be something like a category, we have to have a way of composing morphisms. So the way we'll do that is, let's take a morphism from L2 to L1 called A, another from L1 to L0, and I'd better tell you how to compute the coefficient of some other intersection point C of L2 and L0 in the composition of A and B. So we'll do that by counting rigid pseudo-holomorphic disks. And by that I mean a map from a thrice punctured disk like this one here to M with boundary conditions specified by the Lagrangians. And I want the asymptotes as you approach the punctures to be A, B, and C. So this sort of hollow point is going to represent the sort of output puncture from now on. Now, Crumb's composition is not associative, so this is actually not a category. But you can recover something because the failure of composition to be associative is governed by a ternary operation. And there's a whole slew of coherences amongst a collection of d-area composition operations. And we're going to call those mu d. And in fact, not only that, but these mu d's are given in exactly the same way as composition, except that instead of looking at thrice punctured disks, we'll look at d+1 punctured disks. So that means that the Fukai category is an A infinity category. And an important thing is that this isn't just like an accident of algebra. It reflects the underlying geometry of the domain moduli spaces. And what I mean when I say domain moduli spaces is if we're looking at mu d, for instance, we're defining that by counting maps from a d+1 punctured disk to M. But we're not fixing the positions of those d+1 points. So there's this whole space of possible domains. And let's give that a name. Let's call that KD. So what we're doing is we're looking at all the possible configurations of d+1 punctures on a disk up to by holomorphic equivalence, and then compactifying that. We compactify by saying that if points collide, we remember the fashion in which they collided. And here's a picture of the first 3 of these things. So for K2, for thrice punctured disks, if we have any 2 different triples of points on the boundary of a circle, of a disk, I mean, we can take one to the other by a Mobius transformation. So that means that K2 is just a single point. For K3, we can fix 3 of those points, but we have 1 left over. So that's a 1-dimensional thing. In fact, fact is just an interval, and the endpoints of the interval correspond to either the middle and top mark points colliding, so you sprout this bubble, or the bottom and middle points colliding, and so forth and so on. K4 is a pentagon, K5 is some polyhedron, and each of these moduli corresponds to one of the relations involving the mu d's. So K2 tells you that mu2 is a chain map with respect to mu1. There's sort of a preliminary relation that mu1 squared is 0, so you can regard it as a differential. K3 tells you that, well, these 2 points correspond to the 2 different ways of composing mu2 with itself, and the failure of mu2 to be associative is governed by mu3. Okay. So the upshot of all of this is that it's the geometry of these domains that's giving rise to this algebraic structure. And this is sort of a warm-up for a couple of more complicated domain moduli spaces that we'll see in a minute. Now, one obstacle to computation of the Fukaya category is that there's not an obvious notion of functoriality baked into the definition. So in a series of papers in the 2000s, Mao, Verheim, and Woodward proposed a way of dealing with that. They defined something called pseudo-holomorphic quilts, and they counted these things in order to build this machinery to take as input a Lagrangian and a product, a Lagrangian correspondence, and produce from that a functor from the Fukaya category of one of those manifolds to the Fukaya category of the other one. Now, there are some reasons why this is not the whole story of functoriality, and that led me to build on their work and also some old ideas of Alan Weinstein to propose a structure called SIMP, which is a so-called A infinity 2 category, which has as objects a wide collection of symplectic manifolds. So the objects are M's, and the Hom from one symplectic manifold to another is the Fukaya category of their product. And I'm not going to get any deeper into that particular object, but I will just say that I think it's the right kind of ultimate structure for functoriality. It's also a rather complicated structure and still largely conjectural, and that leads you to want to extract some kind of concrete, down-to-earth consequence of it. So that's the kind of context and motivation for the second part of my talk. So, which trees in the Kontsevich operad? I'll tell you about 2 moduli spaces, which you should think of as analogous to these spaces KD we were talking about before, the domain moduli spaces for the structure maps in the Fukaya category. The first one is called a moduli space of which balls. I won't tell you why. So here's which 1, 1, 1. We're looking at spheres with 3 circles on them. They intersect tangentially at the south pole, and they each have 1 mark point. So we're not fixing the modulus of those circles and those mark points. They can move around. We study those up to by holomorphic equivalence and then compactify. And you could do this not just for the sequence 1, 1, 1, but any sequence of non-negative integers by putting, well, if n is a vector of d non-negative integers, put d circles on a sphere and ni mark points on the ith circle. And I'll tell you more about this in a minute, but let me also introduce, I don't know what quite the right name is, but let's call them the Kontsevich spaces. So we have one for every d at least 2. And the way that cont d is defined is we're going to look at a sphere with d plus 1 mark points on it. This equator here is not a datum. It's just to indicate that this is a sphere, not a disk. And we're going to frame the d plus 1th mark point. So we equip it with a ray in its tangent space, this little arrow. And then we'll look at those up to equivalence and compactify. In case anyone is curious, it's not the same thing as looking at M0 d plus 1 bar and then crossing with S1. So now a little bit of a closer look at these which spaces. Here's a basic example, which 0, 0, 1. So we have 3 circles on the sphere, and we have a mark point on the rightmost circle. And we can fix all of these data using Mobius transformations, except for, let's say, the position of the middle circle. So we have this one-dimensional space, and the endpoints of the interval correspond to that middle circle, the one between the yellow and the blue, colliding either with the left circle or the right circle. Now, the relevance of these things, the kind of structure you get by looking at operations with this as the domain moduli space, is that these are giving rise to the composition operations in simp, this symplectic A infinity 2 category. And something that I'm writing up right now is that you can realize these as compact manifolds with generalized corners, where generalized corners means basically polyhedral type corners. I'll show you one more complicated example. This is actually P111, or I should say which111. So this is a three-dimensional thing, and the way you'd build it, if you wanted to build your own, which you can do, is you'd cut it out along the edges and then identify like-numbered edges. Okay. It's in my office.
Until I see it, it doesn't exist.
Okay. All right. Yeah. So apparently at Jim Stasheff's defense, he brought curvilinear models of his things, and then I think Milner asked a similar question, and then Milner went on to show that they're actually realizable as polytopes. You could do the same thing, because this one, if you folded it up, is actually curvilinear. So, okay. So the point of this is just that you can see that this is kind of a rich-looking object with some interesting combinatorics.
You mean that one is space is toward right?
No. In the moduli space, I'm not sure. Maybe we can talk afterward. Okay, and now a closer look at these Kontsevich spaces. Here's a simple example. The third Kontsevich space is just S3 minus the neighborhood of a three-component link. Three-component link because of the three possible ways of the points splitting up into pairs and colliding. So the relevance of these spaces is that if you come up with good cell decompositions of these spaces, you could lift the structure on another important invariant in symplectic geometry, the symplectic cohomology of an exact. Haber algebra is. But I will say that one reason that you might believe that this is something that you might care about is that it's an analog of a roughly 25, 23-year-old conjecture of Professor Deligne, which is that there's this other invariant of something completely different, Hochschild cohomology of an associative algebra. And Professor Deligne conjectured that, or asked whether this Gersten-Haber structure on Hochschild cohomology could be lifted to the chain level. And not only was that solved over the course of about 10 years, but it spawned a number of interesting research directions. And now this is the part where I was saying that it'd be nice to extract some kind of concrete consequence out of the putative existence of SIMP. And something that its existence would suggest is that we should really be able to come up with these good cell structures on these Kontsevich spaces. And I'll tell you how I think that that could be done. Here's the connection between these which spaces and Kontsevich spaces. We have maps that go from spaces of which balls with one marked point on each seam to these Kontsevich spaces. And I'll tell you how it works. Here's a point in which 111. We're going to forget these three circles, but we'll remember one thing about them. We're going to use them to cook up a framing of the output marked point by labeling it with an arrow parallel to these three circles. So we'll get this guy here in Kont 3. And now let's look at the image of this map. So here's which 111. And remember that Kont 3 is S3 minus 3 circles. And let's picture that by stereographic projection as R3 minus some things. Here's the image. So this is a hemisphere that you cut out a half cylinder from the front and a sort of curved half cylinder from the back. And then you sort of form little spikes or cusps at these 4 points. And that sure looks like a cell. And in fact, if you look at the 6 maps you get in this fashion, corresponding to the 6 permutations of 1, 2, 3, you do get a cell decomposition of Kont 3. So then I'll close with this conjecture, the obvious conjecture that you really can use these to cook up cell decompositions of the Kontsevich spaces, which fit well with one another. And the top cells in the Kontsevich spaces are just the diffeomorphic images of the interiors of these wishball spaces. So this is something that I'm hoping to prove this year, and if anyone is in the mood for some pleasant topology and combinatorics, I'd be happy to have a collaborator. So thanks for your attention.